All right, ladies and gentlemen, it is time to get into some very high-powered theoretical mathematics that is going to allow us to find zeros for any polynomial and hence factor any polynomial without using any sort of technology whatsoever. So we're going to start out simple. We're going to start out with just integer zeros, start out by finding those, and then we'll move into finding rational zeros and then beyond. So our first theorem is the integer zero theorem. It says given a polynomial f of x, there's our normal generic polynomial f of x, where a sub k is an element of the integers. So we're talking about polynomials with integer coefficients and a leading coefficient that is not zero, and an integer p such that f of p equals 0. Then p is a factor of the constant term. So what we know is that there is a value p, an integer, such that f of p is 0. So p is a 0 of this polynomial, and if there's a 0, then p has to be a factor of that. Okay, so let's prove it. Let's show that this is true. So f of p would be an p to the n plus an minus 1 p to the n minus 1 plus yada 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 plus a1p plus a0. We know that equals 0. We're told that p is going to be a 0 of this polynomial. So if we move the constant term to the other side, now everything on the left side has a factor of p in it. So factor out the p. And we've just shown that p has to be a factor of a sub 0, because we've written a sub 0 as the product of p and something else. Now a corollary from this theorem, corollary means it's something just as important that follows immediately from the original theorem. So this says if we have a polynomial f of x, where a sub k, the coefficients are integers, and the leading coefficient isn't 0, and an integer p such that f of p is 0, you know, that looks pretty similar, then for any integer value q, p minus q will be a factor of f of q. Okay, so mind might be hurting right now. You might have gone a little bit numb from this. Lots of words, no numbers. What does this all mean? Well, bear with me here. Let's prove that this is true, and then we're going to do an example that I think is going to illustrate very clearly how this works and why it's even useful. Because just looking at this, you might be going, who cares? I know I do when I first look at it. So here's our proof. F of p is equal to an p to the n plus an minus 1 p to the n minus 1 plus yada 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 plus a1p plus a0 equals 0. F of q, that's going to be an q to the n plus an minus 1 q to the n minus 1 plus da 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 plus a1q plus a0, and we don't know what that equals. Let's subtract. So now we have f of p minus f of q. And if I group the terms that have the same coefficients here, we can factor out. So an times p to the n minus q to the n plus an minus 1 p to the n minus 1 q minus q n minus 1 plus yada 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 plus a1 times p minus q plus the a zeros go away. Okay, so we know that f of p is equal to 0. So the left-hand side is negative f of q. And on the right-hand side, since every term is p to the n minus q to the n, or p to something minus q to that something, it can be shown, and we're not going to do this, but it can be shown. Let me dive down here a little ways. It can be shown that a to the n minus b to the n is divisible by a minus b for all positive integers. So that's something, if you're curious, go ahead and give it a try, prove that. But that's something that is provable and known to be true. So every single one of these terms has a factor of p minus q. So since every term on the right-hand side has a factor of p minus q, p minus q is a factor of f of q. And that's what we were trying to prove. Now, one more thing to look at before we get into the meaty goodness of an example, and it is called Descartes' rule of sign changes. And what it tells us is that the number of positive real roots will be equal to the number of sign changes between the coefficients of f of x, or an even number less. Okay, so, what? What does that even mean? If we look at this example, what we find is that the terms go positive, negative, negative, positive. There are two sign changes there. And according to this rule, there will either be two positive roots or an even number less than that, or 0 positive roots. Now, the other side of this, we can also know the number of negative real roots. That will be equal to the number of sign changes of f of negative x, or an even number less. So if I find f of negative x, so the first term is going to be negative 2x to the third minus 3x squared plus x plus 1. Now the signs are going negative, negative, positive, positive. There's one sign change. So there's one negative root, or an even number less, so or 0 negative roots. Okay, so let's put this into practice. Oh boy, here we go. Let's see if we can't make heads or tail of this. Find all the positive integer zeros. Find all the possible integer zeros of this function f of x. Okay, so using our integer zero theorem, we know that p, an integer 0, has to come from the list of factors of the constant term. So it could be plus or minus 1, plus or minus 2, plus or minus 3, 6, 9, or 18. And what we could do is we could just check each one of these using synthetic division and see if we end up with one that's 0 as a remainder. We could, great, awesome, but there's got to be a better way. So what we're going to do is we're going to use the corollary that we saw. By the corollary, we're going to pick some value for Q. And it doesn't really matter. Some values of Q are going to yield better results than others, but I'm going to let Q equal 1. 1's an easy number to plug in. F of 1, we can very quickly get that F of 1 is equal to 3. So, by that corollary, P minus 1 is a factor of 3. The corollary said that P minus Q will be a factor of F of Q. Okay, so what are the factors of 3? The factors of 3 are plus or minus 1, plus or minus 3. So P minus 1 has to equal that. So P, if I add 1 to each of these possible factors of 3, we get P, it could be 2, 4, negative 2, or 0. I just added 1 to positive 1, positive 3, negative 1, and negative 3. So from the theorem, we know that P has to be one of these numbers. From the corollary, we know that P has to be one of these numbers down here. So what do they have in common? Well, these two lists have in common positive 2 and negative 2. So P is either positive 2 or negative 2. One way to figure it out now is we could do synthetic division. We could do it with positive 2. 1, negative 7, negative 9, 18, go 2, and look at what we get for the remainder. If 0 is the remainder, cool. Positive 2 is a 0 of that polynomial. Then we check the negative 2. We could also use Descartes' rule of sign changes. For our polynomial, the signs are going positive, negative, negative, positive. So there's 2 positive roots, or 0. And since we only have 2 choices, we have positive 2 or negative 2, there's 0 positive roots. And by default, that should say that it's probably going to be this, but we should double check. What is f of negative x going to give us for signs? For signs, we'll get negative, negative, positive, positive. So here we know that there's 1 negative root or 0 negative roots. So by Descartes' rule of sign changes, it tells me that this is the only integer root that we could have.